In B, more gas B is added to the container. In this one, we can kind of expect to be different. When we add B to the container, because the order is 0, there will be no change. An increase in concentration of B would have no impact on the rate. And the reason is because the order with respect to B is 0. I think that does cover our Y, but this is the extra bit which I'm not sure. I would definitely add it. The reason B is 0, even though it's needed in the reaction, is because this suggests that B is not in the rate limiting step. And that would be the reason why it wouldn't impact the rate. So the black part is definitely, I would recommend it. And then I only talked about the rate up here, so the rate constant, again, would not change because we're not changing anything other than the concentrations. In part C, the temperature is increased. Well, we know as the temperature increases, the rate often increases. The important thing here is you'll notice that not only would the rate increase, but the rate constant would increase too, because temperature does impact K. So the rate would increase because a larger percentage of the molecules would collide with sufficient energy to overcome the energy of activation. So here I felt there was really no way to avoid doing a collision theory argument. So definitely going to need this part here. It wouldn't be enough just to say, well, because the temperature went up. You'd have to talk about collision theory. And then part D, an inert gas, D, is added to the container. You notice the inert gas is not in the equation. So remember, inert gases can be a little bit tricky. They definitely do not affect the rate, nor would they shift the equilibrium if we were talking about equilibrium. Inert means does not react with anything in there. That's what inert means. Like the noble gases are inert gases. So an inert gas would have no impact on the rate or rate constant, since it does not impact the partial pressure or concentration of A or B. As you remember, you might think, well, if you're adding more stuff in there, that's going to increase the pressure. That's true, but it doesn't increase the partial pressure of A. It doesn't change the concentration of A within the container. There's still the same number of dots or molecules of A in the same volume. So it's not going to impact the concentration. And then E, the volume of the container is decreased. And you remember that a decrease in the volume of the container will cause an increase in the concentration because you're shrinking the size of the vessel, so everything's got to be sort of jammed in there more tightly. So making this relationship between change in volume and increase in concentration is important, because once you get to that point, of course, increasing the concentration of A will increase the rate, but will not change the rate constant. And I don't feel like I need to say much reasoning here, because it's the exact same thing that we were talking about in Part A. So I just said the reasoning is the same as Part A, and I think that's good enough. One last point is this business about referring back to something earlier. I can refer back to A as part of my supporting argument because one AP grader grades this whole question. But I wouldn't want to say, well, hey, look back in question 2, part C, because that's a different grader. They are not going to be able to find your paper at the other table. So only refer back to work you did within a question.